Good morning. I would like to present to you the topic of overall binding leathers. Thank you. Especially the possibilities and limitations of removing leather dressings using laser radiation, which should give you a quite heavily summarized overview of the research of my master thesis. For decades, leather dressings were applied to leather bindings amongst other objects, in the belief that this would benefit their preservation. While this practice was well-intentioned, today we are confronted with its unintended consequences. Overall binding leathers form a common conservation issue, resulting in the need for a safe method of removal. Within my thesis, I examined the potential of using laser radiation at a wavelength of 1064 nanometers for their removal. Written sources on applying leather dressings to leather bindings within the context of conservation date back to the 19th century. By the early 20th century, the practice had already been implemented by the personnel in larger collections. Generous, repeated, and systematic dressing of leather bindings became a standard. Concerns and critical opinions were mostly just met with new recipe variations. The variety of leather dressings was immense, both commercially available as well as self-mixed ones. They generally contained lipids, that is, oils and/or waxes, some type of solvent, and optionally additives like emulsifiers, fungicides, pesticides, and antioxidants. In general, dressings were thought and meant to preserve the leather, improve and maintain its physical characteristics, such as flexibility and elasticity, protect it against environmental factors, produce a chemical stabilization, and last but not least, improve the leather's optical appearance by enriching the color and creating a perceived gloss effect, for instance. However, the actual negative consequences for overly dressed binding leathers have shown themselves to be just as impressive, such as accelerated degradation, dehydration, embrittlement, hardening, shrinkage, microbial infestation, spew formation due to fatty acids, darkening, discoloration, and tackiness, which also means attracting dust and can even mean books being stuck together, leading to physical damages. So there will be quite a number of cases where removing leather dressings, or specifically oils and waxes from leather bindings, becomes necessary. Typically, the course of action would involve the use of solvents in some way in order to extract the lipids and/or clean the grain surfaces. Depending on the exact technique and leather, the results might be quite satisfactory, but up to that point, it can be a lengthy process as well as a messy one. Additionally, complications like an uncontrolled redistribution of lipids, difficulty controlling how much lipids are actually removed, discoloration, and a change of the leather surface might occur. And last but not least, health concerns for the treating conservator need to be taken into account. At that point, my master thesis comes into play, as I examined the question whether laser radiation could potentially be used as an alternative for removing leather dressings from binding leathers. Laser cleaning has been used in conservation for several decades already, and over time the range of materials and purposes for which laser radiation can be applied has steadily expanded. Today, many different laser systems are available, each tailored to the requirements of specific applications and materials. In essence, laser cleaning refers to controlled material ablation. A laser beam is directed onto a surface where it is absorbed, at least to some degree, by the unwanted material. Depending on the mechanism, this absorbed energy leads to the ablation, in other words, the removal of the contaminant. Without going into the technical details of the different mechanisms, some general advantages are often cited for laser cleaning. First, it is a contact-free method and does not exert any mechanical impact, which makes it highly suitable also for sensitive materials. It can be applied in a very selective and precise manner, targeting surface residues without affecting adjacent areas. The process can be carried out entirely without solvents, and in certain cases it is even self-limiting, which is when the residue absorbs more laser radiation than the underlying surface. The ablation efficiency decreases once the residue has been removed. Prior to the main experiments, I did some pre-tests using a variety of leather dressings, applied to historical as well as modern samples. Based on the preliminary observations, I then decided on a two-part experimental design. On the one hand, I used modern vegetable tanned leather, which was artificially aged before further preparation. These samples provided a uniform test material and thus allowed for better comparative examination. On the other hand, I obtained 13.5 vegetable tanned leather bindings from the 18th century, which provided 27 samples in total, since each cover was treated as one sample. Naturally, these historical leathers displayed a wide range of aging conditions and surface characteristics, including various damages. For the experiments, I selected two types of leather dressings. One, the British Museum leather dressing, of which the main ingredient is lanolin, and also the commercially available Sear 213, which primarily contains of neat's foot oil. The samples were divided into 9 categories for preparation. Some were artificially soiled, some were treated with one of the dressings, and others received a combination of a dressing and artificial soil. Including soil, the test was intended to explore whether the dirt might have any influence on the success of laser removal of leather dressings. The laser treatment was performed with a Q-switched neodymium YAG laser operating at 1064 nanometers. 6 basic parameter settings were defined, differing in pulse energy and repetition rates. Within each setting, the fluence was gradually adjusted to determine 2 critical energy densities. First, the ablation threshold, meaning the lowest energy density at which a noticeable amount of dressing is removed. And second, the damage threshold, which is the lowest energy density at which laser-induced damage to the leather could be observed. Each sample was masked with a cardboard stencil that defined fields of about 1 square centimeter. In total, a little over 3,000 test fields were irradiated, around 1,200 on the modern samples and 1,800 on the historical samples. To ensure consistent working distances between the laser handpiece and the sample surfaces, I built a continuously height-adjustable setup. This construction can be seen in the image on the left, while the complete laser setup is shown on the right. Since the focus was on examining a large number of test fields, the primary method of analysis relied on visual assessment, both macro and microscopic under varying lighting conditions. The margins of the test fields proved particularly useful as they clearly defined the edges between irradiated and reference areas. In addition, selected samples were examined with 3D profilometry to gain a closer understanding of the surface topography, especially on the cleaning effect in relation to the pores. Some of the flaked-off ablation products, such as the white flakes shown in the upper image, were analyzed using ATR, FTIR to investigate the ablated components. Furthermore, shrinkage temperatures were determined for some test fields and compared to reference samples in order to check whether laser-induced changes could be detected. 2 main ablation mechanisms could be observed during the experiments. The first is photothermal ablation, which occurs when laser radiation rapidly heats the target material, causing either direct sublimation or melting followed by evaporation. Signs of evaporation and sublimation were observed in most of the test fields, though they were much more pronounced with Ca-213. This effect can be attributed to the neatsfoot oil it contains. Proving and quantifying this type of ablation, however, is quite challenging. The second mechanism is thermomechanical ablation. In this case, rapid energy absorption leads to mechanical stress within the material, resulting in flaking and detachment of macroscopic particles. This can be seen in the test fields with formerly transparent leather dressings turned opaque and then being ablated as white flakes. This mechanism was observed with waxes, including lanolin. It was also a very satisfying effect to observe. Much less exciting were the laser results for the modern samples. Overall, they showed inconsistent responses and relatively little cleaning success. However, one significant finding was the influence of combining artificial soiling with the leather dressings, which became clearly visible in these 3 examples. All 3 samples on this slide were treated with British Museum leather dressing. The first sample on the left was only treated with the dressing, the middle one was artificially soiled beforehand, and the third sample on the right was soiled afterwards. For the unsoiled sample on the left, almost no ablation could be achieved, and what little did occur happened only very close to the damage threshold. In practice, that means playing with fire, as the working range for the laser settings is incredibly small. The middle sample instead showed significant ablation, even from very low energy densities. That being said, complete ablation, meaning a complete removal of visible leather dressing, was not possible, which was actually true for all modern samples. The sample on the right proved just as disappointing as the one on the left, even though it seems much more successful at first glance. But the laser radiation removed only the dirt layer, while the ablation of the leather dressing only happened to a similar degree as for the left sample. The historical samples generally yielded much better results, with low ablation and high damage thresholds, leaving large ranges of usable laser parameters. The only significant exception was seen with 2 bindings with severe surface degradation, as they showed unusually low damage thresholds, complicating the laser treatment. Interestingly, the strong influence of artificial soil on laser treatment of the modern samples could not be verified with the historical samples. The 2 bindings shown on this slide are nearly identical in aging conditions, surface morphology, and so on. But the one on the left was first artificially soiled and then treated with British Museum leather dressing, while the one on the right was prepared in the opposite order. Still, they showed almost identical response to the laser radiation. As can be seen, almost all test fields achieved significant or even complete ablation. The gradual change of energy densities for the tests resulted in varying degrees of ablation and damages, of which you can see 3 different states on this slide. The first image in the upper left corner shows the very first signs of ablation. Some parts of the laser-treated site have turned opaque, but they are still attached to the leather surface and cannot be successfully removed. With the middle example, you can see the contrast between the left reference site and the irradiated site showing nearly perfect ablation, with only small residues left. The image in the lower right corner likewise shows a very neatly ablated test field in the right half of the image. But as you can clearly see, the surface also displays laser-induced damages, which is, of course, not the desired outcome. The different consequences of laser cleaning on the leather surfaces can also be seen through 3D profilometry. The upper image shows a thick layer of leather dressing on the sample's left side, and a successfully cleaned right side with once again visible grain layer, including even mostly clean pores. The lower image instead displays the contrast of the reference side with a thick layer of leather dressing to the other side, which has been irradiated at a setting above the damage threshold. You can see how the grain layer has been ripped to shreds and bears no resemblance to the upper example. Apart from damaged leather surfaces, one very frightening phenomenon occurred in some test fields, namely melted leather dressing. Instead of flaking off or not reacting at all, the dressing in these cases simply melted and then remained on the leather surface, which you can see on the right side of the image. Naturally, this rang a lot of alarm bells, but some things also became clear during its investigation. This phenomenon only happened on a small number of test fields and only on very dark leathers, or leathers with dark discolorations. Then I also took fiber samples from the leather directly below the melted leather dressings and measured the shrinkage temperatures. Luckily, they were the same as compared to the references, so no apparent damage to the leather could be detected, but the result of the melted dressing is, of course, still not desirable. Interestingly, only the British Museum leather dressing exhibits this reaction and it is most likely caused by the lanolin, which has a melting point of about 36 to 40 degrees. And this has obviously been reached in these examples. The heating apparently only happens within the dressing layer though, as one leather in question has a shrinkage temperature of around 32 degrees, but yet did not get damaged by the melting whatsoever. In any case, the combination of dark leather surfaces, leather dressings containing lanolin, and laser radiation, especially at high repetition rates, should be treated very carefully. Despite this phenomenon, removing leather dressings from vegetable tanned leather surfaces using laser radiation generally appears to be a splendid idea. The overall results on historical samples showed the significant potential and advantages of this method, while still leaving room for much more experiments and research. Last but not least, I would like to thank everyone who supported my thesis and consequently me, and thank you all for your attention.